Maps, along with cross-sections, are one of the most fundamental tools of the exploration geologist. And in this module, we're going to see how subsurface maps are made and used. In Unit 1, we'll look briefly at the ways we gather subsurface information. After all, it is the first step in map making. In Unit 2, we'll consider contour maps and methods, and the various kinds of contoured surfaces and units that are especially important. We'll also look at one of the most widely used subsurface maps, the structural contour map. Finally, in Unit 3, we'll discuss just a few of the many other types of subsurface maps that are particularly useful to both the exploration and production geologists.
In this technological age of ours, science has created incredible tools with which to view our world. Sophisticated microscopes that can see down into the size ranges of atoms, and powerful telescopes that can look at distant worlds similar to our own. The exploration geologist has to see through solid rock, thousands of meters into the subsurface, where still the only direct information is obtained through boreholes into the earth. The job of the geologist is to fix a drilling location that is only able to sample a minute part of the Earth's subsurface, either directly through cuttings and cores, or indirectly through measurement tools that can be lowered down into the borehole. Subsurface techniques use the same parameters as surface geologic methods, but they don't have the benefit of lateral continuity, unlike rocks at the Earth's surface. It's part of the job of the exploration geologist to extrapolate data from boreholes only a few tens of centimeters in diameter over distances that may exceed tens of kilometers. In other words, to create subsurface maps. Of course, exploration geologists undertake these exercises not as ends in themselves, but in the hope that some of the maps will display anomalies, which may point to the presence of undiscovered oil and gas fields. Oil is where you find it, but in known producing provinces, subsurface mapping has proved successful in guiding the drill towards the more promising areas. In describing the subsurface in map form, the petroleum geologist tends to be optimistic, and the act of mapping expresses his perennial confidence that something will turn up. Of course, geologists cannot go down a hole to obtain our subsurface data. More conventional means are used. Nearly all modern holes are drilled with rotary tools, usually using mud as the drilling fluid and cutting carrier. The kinds of well logs we can make through rotary drilling fall into three main categories: wireline logs, drill cuttings logs, and mud logs. Wireline logs are produced by a variety of physical signals, recorded by instruments and electrodes, contained within a fluid-proof metal container called a sonde. The sonde is lowered rapidly to the bottom of the open borehole. It is then slowly raised back to the surface, continuously transmitting measurements up the conductor wires to a logging truck, where they are recorded onto a moving strip of film. There are three main types of wireline logging: electric, nuclear, and acoustic. Electric logging is the cornerstone of wireline logging services. It may actually encompass 8 or more different measurements involving a formation's electrical resistivity and its spontaneous potential, or SP. These electric logs, together with other wireline logs and cutting samples, provide useful information in identifying and correlating lithologies, and in determining porosity, water or petroleum saturation, and in some cases, permeability. The dip angle of inclined strata can be determined by a special variation of electric logging techniques, the dip meter. It's based on the simple principle of nonlinear points, in this case, the logged records of 4 electrodes, defining a plane. Important nuclear logs are the gamma-ray log, which records the natural radioactivity within different rock types, the neutron log, which measures hydrogen-filled porosity, and the formation density log, which is also useful as a porosity logging tool. Acoustic velocity logs record the travel time of sound waves through rocks. These mainly reflect variations in the elastic properties of rocks and their contained fluids, and have proven particularly useful in evaluating formation porosity. Wireline logs can give us important clues to depositional environments, particularly in the case of clastic sequences. For example, they can be used to distinguish between coarsening upward bar sands and fining upward channel sands. As a rule of thumb, wireline data that pertains to lithology are displayed on the left-hand sides of logs, and those related to fluid saturation and rock properties, like porosity, are on the right. Now that we have looked at how we obtain data in the subsurface by means of logs, let's look at what we can do with it back at the surface. We can look at drill cuttings brought up by the returning stream of drilling mud. Samples are collected at the shale shaker or in a setting box, bagged and labeled at regular intervals, and then they're examined microscopically. The percentage of different rock types is systematically recorded for each depth interval, and the results are plotted on a sample log, sometimes called a stratigraphic or strip log. The sample log can help us determine lithologic breaks and define stratigraphic units, but it must be coordinated with wireline log data in order to work out details of facies, thickness, and interfingering relationships between two or more different rock types. In some areas, for instance, where the lithology is homogeneous or repetitious, cuttings may be used mainly to produce logs that record biostratigraphic data, reflecting systematic changes in the microfossil content of the samples. For example, this evolutionary sequence of fusilinids. It's important to remember that there is a lag time between the chipping of samples by the drill and their return to the surface, and this may amount to several hours for deep wells. Sample and fossil logs must always be corrected to reflect the true depth of sampling. Knowing the capacity of the mud pump, the pumping rate and size of the hole, this lag time can be calculated, or it can be measured directly by adding tracers to the mud stream that are easily detected when they come back up. Uncased walls of the hole with less consolidated and fractured lithologies commonly collapse and contaminate drill core cuttings from deeper parts of the well. Consequently, the first appearance of a distinctive lithology or fossil is obviously something new, not the result of caving, and may be particularly important in reconstructing the borehole stratigraphy. However, since cavings may have a larger size and different appearance than the rest of the cuttings, an experienced sample examiner is often able to disregard them. Cores may be cut when specific lithologic or reservoir information is needed. Obviously, a core is preferable to cuttings because it produces a coherent section of rock for detailed examination and testing. However, cores are significantly more expensive to obtain, and a major difficulty for the petroleum geologist is knowing just when to core. Mud logging, as its name implies, involves the continual inspection of the drilling mud. It mainly records such data as the rate of penetration of the drill bit, sample lithology, and, most importantly, shows of oil and gas in both the cuttings and the mud. There are holes today that are still sunk using cable tool drilling methods, although rotary drills are more common. The cable tool consists of a wire rope suspending a cylindrical bit with a chisel-like end. This is lifted and allowed to fall back to the bottom of the hole repeatedly. The resulting rock chips are removed with a baler.
Now, these cuttings are recovered and significant formation fluids are sampled after each baling with the data recorded on what's called a driller's log. Now, since the new hole rapidly fills up with chips, this usually occurs every few meters. So there is no lag time, and the depths recorded are very accurate. In older petroleum provinces, geologists creating subsurface maps can't ignore driller's logs, since cable tool drilling was the most common method used prior to World War II. The language of 50 to 75-year-old driller's logs is not very geological, true, but they're generally reliable when it comes to locating major formation boundaries and lithology changes. and in most cases shows if water, oil, and gas are precisely recorded as to the depth, the quality, and quantity. Now, most major oil companies maintain complete in-house libraries of subsurface data, but the smaller companies and independent operators today rely heavily on the existence of log libraries in all important centers of exploration. Many of these are commercial log libraries, but some oil-producing states and governments maintain libraries of drillers and wireline logs, production records, and sometimes cutting samples, and cores for public examination. Now, if a log library isn't convenient, or you need a file copy of the logs and scout reports, you can obtain this data commercially on microfiche. And all the essential information from mapping an entire province can be kept on file in your own office.
We must not assume that all of this data came from vertical holes. Obviously, there are situations where it's impossible or not feasible to drill a vertical hole, as when the subsurface reservoir is beneath a lake, river, or in a metropolitan area. In such cases, the drilling rig is set at a more convenient location, and the hole is deviated to reach the reservoir. In the early days of drilling, many wells were quite unintentionally deflected, what we call a crooked hole. Crooked holes are still a concern in regions of structural deformation and steep dips, where a vertical hole tends to deviate in a direction perpendicular to bedding. In offshore provinces, it's usually economical to drill several wells from a common drilling platform, all but one of which will deviate from the vertical. The engineering technology involved in controlled directional drilling is complex and beyond the scope of this module. But the subsurface geologist must be able to use information from such wells to correct for true vertical depths of correlation points, true bed thicknesses, and true map coordinates of points in the subsurface. This information can be obtained by the use of special wireline directional surveys or from data obtained in a dip meter.
Now, if we're careful, logs made from slanted drill holes can be corrected so that every lithologic marker will fall at its true vertical depth and its proper location. Then we'll be able to incorporate that data into vertical cross-sections or structural contour maps. But that's a topic for the next unit. So read the manual and do exercises 1 through 5 at the end. Now that we have seen how subsurface information is obtained and have looked at the different kinds of logs which we get with different drilling methods, let's turn our attention to using this information in the making of subsurface maps.
Groups of logs within a region display distinctive thin sequences, key beds, or similar configurations and kicks on log curves, all of which can be used as correlation points for subsurface maps and cross-sections. Some of these features may be quite local, but the most useful correlation points are those recognized over large parts of a petroleum province. For example, the top of a widespread blanket sandstone formation. A strong effort should be made in recognizing log markers that are both reliable and regionally continuous. In some areas of the Gulf Coast of the United States, marine transgressions were usually abrupt, and vertical changes from sand to shale lithologies are sharp. These boundaries often make excellent regional markers on electric logs and are particularly useful since they lie just above extensive sands with good reservoir potential. Similar abrupt transgressions are found in many oil provinces, as, for example, the Cretaceous clastic sequence of the Western Interior Seaway in the western part of North America. However, in other areas of the Gulf Coast, for example, Louisiana, where rapid deposition took place in deltaic environments, the thickness and aerial extent of individual sand bodies is highly variable. In these areas, thin line stringers with characteristic resistivity signatures must be used as correlation markers. They often result from deposition during periodic intervals of quiet, low-energy conditions, and therefore tend to be more widespread than individual sand bodies. A vertical change recorded on a log can be viewed as either a physical boundary separating two distinctive bodies of rock, like this boundary between sand and shale, or it can be viewed as a visible trace of an abstract geologic event, say the change from shallow to deep marine deposition. In either case, the logged points are just a few of a vast number of such points that generate a three-dimensional surface, a lithologic surface, if it separates two different rock types. We can also define time rock surfaces, which separate all rocks younger than a specified age from those that are older. Time rock surfaces are usually not defined by identical log markers, since facies shift laterally in space through time. Log markers usually define a lithologic surface, even though a comparison of cuttings and wireline curves from the same depth does not always satisfactorily account for the cause of the marker. The notable exception is the paleontologic log, which reflects evolutionary changes in fossil assemblages, and by and large defines a time rock surface. In some cases, lithologic breaks can occur almost instantaneously over large areas. A striking example of this occurs when a volcanic eruption leads to the deposition of a bentonite bed. This, too, represents a kind of time rock marker. It's clear that the basis for all correlation work and mapping is the recognition and definition of markers. 3 or more of these marker points can be used to construct a surface, and once 2 surfaces have been described, they can be used as boundaries to define and enclose units. These can be either rock units, such as a formation if enclosed by lithologic surfaces, time rock units, such as stages and series if enclosed by time rock surfaces, or any arbitrary division that we find useful. The unit has always been regarded as the basic concept and traditional stratigraphic usage, and a rigorous international code has been devised to standardize the definition and naming of such units. But the subsurface geologist feels no such compulsion to follow the traditional naming scheme. He's apt to designate mapping surfaces or thickness units by a single letter, a number, some alphanumeric combination, or a paleontological marker. He recognizes that surfaces are a much more fundamental concept, and surfaces can be used to construct a great variety of stratigraphic units, each precisely measured and defined in whatever manner will help him in the search for oil. But speaking of that, let's suppose we've just drilled a dry hole. We must have gone wrong somewhere. Maybe if in our contouring we had connected up the points differently.
And you see, that's the heart of the matter. Once we've gone through the time-consuming process of gathering subsurface data, we still have to extend this knowledge beyond and below the control wells. We must judge the validity of the data and our certainty in the conclusions that can be drawn on our subsurface maps. Now, continuous lines are drawn on the map when the information appears to be good and confidence in its interpretation is high. We use dashed lines when the data or its interpretation becomes more doubtful, with shorter and shorter dashes as the uncertainty increases. The geologist attempts to show anomalies on maps, but he must also express his confidence that an apparent anomaly is real. Subsurface mapping usually improves as the density of data increases. But remember, it's still only an interpretation.
The most valuable tool of the subsurface geologist is the contour map. A contour line is a locus of points, all of which have, or are inferred to have, the same value. Any subsurface data that can be quantified can be used to draw some kind of contour map. But some of the quantities that are particularly important to a petroleum geologist involve elevations of surfaces, thickness of units bounded by surfaces, porosity or permeability within a unit, concentration gradients of subsurface waters, thermal and pressure gradients, lithofacies ratios within an interval, and production rates. Given an array of boreholes, a major consideration in drawing contour lines is how to arrange them. There are some standard rules when drawing contour lines that should be followed. They should honor the data. The lines should be drawn smoothly and as parallel to each other as possible. They must never cross, and they should be close together where gradients are sharp and farther apart where they're gentle. But even within these guidelines, there are many possible choices. Mechanical contouring, which can be programmed into a computer fitted with a mechanical plotter, is one method of constructing contour maps. Contour interval is selected, and contour lines are interpolated with equal spacing and linear slopes between any two control points. This scheme has much to recommend it because it takes the human bias and tedium out of map making. But there are several pitfalls to this method. One shortcoming of this method is that the control wells are drilled in places where someone had expected to find oil, and as we already know, petroleum accumulations are most commonly found in areas of structural anomaly, in anticlines or adjacent to faults. Consequently, the control points are apt to be in places where the actual contour conditions are nonlinear. This can be partly overcome by using computer programs that instruct the mechanical plotter to contour the trend surface and small features separately. A second pitfall is that mechanical contouring tends to mask small structural features, which might be good prospects, and tends to create unrealistically large ones, as seen here. It illustrates some of the problems of mechanical contouring. Here is a mechanically plotted structural contour map drawn on the top of a reservoir. This type of map portrays the subsurface elevation of a marker horizon. This pattern shows a large north-south trending anticline, having two culminations separated by a saddle. But a closer look at the distribution of productive and dry wells shows this structural configuration to be unlikely. In the apparent structural high in the north, oil is being produced at 6,975 feet below sea level. But at the same and higher elevations to the northwest, the reservoir is dry. At an even lower elevation, in the saddle of the structure, two wells are producing gas. Gas is also produced in the southern anticlinal high, but one of the gas wells is at the same elevation as a dry hole. While mechanical contouring methods may in some cases give a useful first approximation of regional structural trends, a geologist's training and fundamental knowledge of a province's structural and depositional environment enables him to apply a realistic bias to the data and correctly interpret the subsurface structure. In this case, he creates a very different mapped pattern, in which the reservoir sand is uniformly south-dipping, but is cut by steep-dipping east-west normal faults. The productive wells are from separate fields, located along different fault blocks. The interpretive contouring on which the structure contour map is based honors all the data and is consistent with the regional geologic model. It also follows another important rule, that the simplest interpretation that fits all the data is usually the best. The great bulk of subsurface mapping is structural contouring. Let's look more closely at what a structural contour map represents. On a structural contour map, the configuration of a marker surface is expressed in terms of its elevation with respect to a horizontal datum surface. This datum is usually sea level. Ordinarily, the elevations on which the contours are drawn are obtained by subtracting from the depth to the marker the surface elevation of the well. This point, in most cases, is not ground level, but level with a rotary table or Kelly bushing on the floor of the rig, since this is the point from which drilling depths and log measurements are recorded. Usually, marker elevations will be negative numbers, that is, below sea level. except for a few petroleum provinces at high altitudes. On the structure contour map, the elevation of the datum is usually shown next to the well, along with information on any faults which intersect the well. A fault with 200 feet of throw at 3,970 feet subsea cuts this well. The total depth of the well is listed at the bottom. Here is a typical structural contour map from an oil field in Oklahoma. The datum is the top of an Ordovician reservoir sand, and the contour interval is 200 feet. It's fairly easy to visualize the structure here. An asymmetric anticline with a steep northeast limb and a gentler southwest flank. Structure contour maps alone are often sufficient to depict the structures in many petroleum provinces. This is particularly true in cratonic settings, where many fields are located on relatively simple, low-relief folds. But most local folds show some faulting, and many traps are defined or limited by faults. Recognition of faults is one of the major problems in subsurface mapping. When situated between borehole control, subsurface faults may be difficult to detect. Usually faults are not adequately revealed by mechanical and computer contouring methods. Here we see a surface that has been contoured by mechanical contouring methods. Both dips and strikes appear erratic in the central part of the area. In such situations, it is often correct to infer the presence of a fault. In this case, contours should be developed independently from the east and west edges of the area, working toward the locality of erratic elevation. When this procedure is followed, the presence of a fault with a throw between 200 and 300 feet is indicated. A vertical fault, as depicted here, appears on structural contour maps as a linear trace, which does not shift laterally with depth. Because they are vertical, or nearly so, such faults are rarely intersected by boreholes. However, in such cases, the presence of vertical faults is often revealed through seismic surveying, or surface mapping. In contrast, a normal fault with an oblique fault plane will frequently be encountered in drilling, and will be recognized by a missing stratigraphic interval. The interval of missing section equals the vertical throw or displacement of the fault. If two wells intersect the same strata, but only one encounters a normal fault, a comparison of their well logs may reveal the missing section. The stratigraphic interval, as seen between A and B, is present in the well log on the left, and is missing from the log of the normally faulted hole on the right. When mapping control points for structural contouring, there will be an area where the normal fault causes our datum surface to be absent. This is called a datum gap, or a cutout zone, because in any well drilled in this zone, the surface we are mapping will be cut out by normal faulting. In map view, the datum gap appears as a linear zone on which no contour lines can be drawn. The width of the datum gap is determined by the amount of dip of the fault plane and the vertical displacement or throw of the fault. In this map, the width of this gap can be determined by solving a simple structural three-point problem, since three wells, not in a straight line, have penetrated the fault plane at elevations of 1,900, 1,400, and 1,700 feet. In this case, the faulted control points all lie within the datum gap, but this is not required. These control points are joined by straight lines. The difference in elevation of the fault plane between well 2 and 3 is 300 feet, and since the contour interval is 100 feet, the line connecting them is divided into 3 equal parts. The difference between wells 1 and 2 is 500 feet, and 5 equal spaces are laid off along that line. Connecting these points of equal elevation gives us contour lines on the fault plane, and the contour spacing reveals the amount of dip. When the fault plane contours are sketched on the map, they intersect structural contours of the same value. The loci of these intersections marks the boundary of the datum gap. In the manual, there are some simple nomograms that will enable you to calculate the vertical cutout and will help you draw cutout zones on structural contour maps. Unlike normal faulting, which causes stratigraphic sections to be missing, reverse faulting causes the interval between A and B to be repeated in wells. This is evident if data from an unfaulted well is available for comparison. Looking at electric logs from these two wells, a prominent kick, seen on the log at the left, is repeated twice in the log of a reverse faulted well on the right. Here is a cross-section showing a high-angle reverse fault that contains oil both above and below the fault plane. In this case, we will need two structural contour maps to properly depict our surface. The line of section runs east-west through the center of our maps. One structural contour map emphasizes the area above the fault plane, and the oil-bearing anticline is clearly indicated. The intersection of the upper trace of the fault plane intersection with the datum is shown as a curved line on the map. Contours to the right of this trace are areas lying below the fault plane, in unrepeated section. On this second structural contour map, we see the marker surface below the fault plane. Its intersection with the fault plane produces the curved lower trace. To the right of this trace, the surface is folded into a syncline, and the upturned edge of its faulted flank has accumulated oil. The distance between the lower and upper traces of the fault plane gives us the horizontal displacement of the marker horizon. As in the case of the normal fault, the reverse fault can be accurately located and contoured if 3 or more control wells intersect the fault plane. Here is a structure section of the Painter Reservoir field in Wyoming. It demonstrates that the situation becomes even more complex in areas of multiple low-angle overthrusts. Structural contours become totally inadequate in describing a marker at the top of the nugget sandstone, except in local areas. Each major thrust slice would require its own contour map, and in such structurally complex areas, cross-sections and block diagrams are usually a better way to depict the area as a whole. Changes in strike and dip, recorded on a dip meter log, may be helpful in confirming the presence of a fault when suitable unfaulted logs are unavailable for comparison. Away from the fault plane, the strata have a uniform dip angle of less than 10 degrees, but bedding steepens gradually to 40 degrees as the fault plane is approached. Below the fault, abrupt changes in both dip angle and orientation occur. The dip changes may result from drag along the fault plane, as in this case, or in the case of growth faulting, from slump or rollover into the fault plane. It may be possible to infer the strike of the fault from such data, as the dips immediately adjacent to the fault intercept are usually perpendicular to the fault strike. Provided the type of fault is known, normal, reverse, or growth, the direction of faulting may be determined. When dips result from fault drag, they point in a direction away from the fault plane in the downthrown block, and towards the fault plane in the upthrown block. In the case of growth faulting, dips in the downthrown block adjacent to the fault intercept point into the fault plane.
There are other logged properties that can be used to detect faults. Shear zones along faults may be detected on mud logs as a result of hydrocarbon saturation, mud gas kicks, or loss of drilling fluids. These zones also may have increased porosity and permeability, which is indicated on acoustic and density logs. Or they may concentrate uranium-bearing minerals that will show up on nuclear logs. And abrupt changes in temperature gradients or even temperature inversions are often found along faults that are still active.
In addition to their effect on logs, the presence of faults in wells may be inferred from fracturing and veining in cores and from slickensides in well cuttings. Here we found some missing section. There must be a normal fault.
Not so fast. You've forgotten all about unconformities. See, the question of whether a gap in the stratigraphic or paleontologic section is the result of a fault or of an unconformity comes up often in subsurface mapping. In fact, it's often impossible to answer from only a few wells. Unconformities are structural surfaces. Now, since some are avenues of secondary migration and others act as traps and seals for reservoirs, they hold considerable interest for the subsurface mapper. But disconformities and low-angle unconformities frequently aren't recognizable in well samples or on electric logs. Now, when this occurs, or when the nature of the unconformity is poorly known, the structural maps that are constructed may not accurately reveal the regional structure.
Here we see low-relief folds buried beneath an unconformity that has considerable topographic expression. The strata below the unconformity looks like a good target, and 4 wells are drilled. But purely by chance, the 2 wells in the high parts of the structure happen to encounter lows on the erosion surface, whereas 2 wells that are structurally low are sited on paleotopographic highs. As a result, the strata below the unconformity are mapped as flat-lying. The underlying structure remains hidden, and drilling was abandoned. In some cases, a marker surface itself may be destroyed by erosion along an unconformity, and the true structural configuration will again be distorted. We can still map and contour the elevation of the top of the underlying formation, but this is not the same as that of the original datum. As a result, on a structural contour map, any contours within the area bounded by the truncated datum will not represent the original structure. Dip meter logs may be useful in revealing angular unconformities. This dip meter log from northern Algeria reveals 2 unconformities that are indicated by electric log. The lower unconformity separates beds dipping 20 to 30 degrees from overlying strata dipping only 10 degrees. The upper unconformity is basically a disconformity, and just above it, beds dip very steeply. This occurs only in the youngest post-unconformity strata, which probably slumped into and infilled the hollows on the erosional surface. Let's take a break and look at the manual.
We've just seen how control points can be contoured to reflect the structural configuration at some level in the subsurface. Now, let's put 2 surfaces together and depict the thickness of the unit that these 2 surfaces enclose. This creates the second most common type of subsurface contour map, the isopack map.
The contour is called an isopack line. It is a line that connects points of equal thickness within the unit interval. In the case of an isopack map, widely spaced lines mean uniform thicknesses, and closely spaced lines represent areas of rapid lateral thickening or thinning. Isopack maps are particularly useful in illustrating the growth of structural features, either folds or faults. Remember that in essence, the isopack map represents an interval between 2 reference surfaces. In a hydrocarbon province today, neither of these surfaces is likely to be horizontal, because oil wells are usually drilled in areas of structural anomaly. But one of the most fundamental rules in geology is that deposition is essentially horizontal. If we unfold the upper reference surface and regard it as a level plane, we can see that the isopack thicknesses reveal the structural attitude of the lower surface at the time the upper was deposited. It's rather like a structural contour map representing some time in the geologic past, except the anticlines are thin strata and the synclines are thick. In the Powder River Basin of Wyoming, productive sandstones lie between a homoclinal bentonite marker and an underlying regional unconformity. Using the bentonite as the upper reference plane, the thickness interval between it and the unconformity reveals the shape of the erosion surfaces. It is marked by river channels, deeply incised into the underlying shale. Although this structure is topographic rather than tectonic, the isopack map shows the structural attitude of the buried unconformity at the time the bentonite was deposited. Thus, this map is useful as a paleotopographic map, indicating the main depositional trend of the sandstone reservoir.
In principle, an isopac map can be constructed directly from the data contained in two structural contour maps, but in practice, the thickness of formations to be mapped are often directly measured off the well logs. This sometimes leads to one of the common sources of error in constructing isopac maps, a stratigraphic thickness that's too great.
A correct stratigraphic thickness for the construction of isopacs can only be measured directly in a straight hole where the beds are level. But most wells are drilled on structures where wells may penetrate formations with appreciable dip. In this case, thicknesses will be measured on inclined strata in either vertical or deviated holes, and will yield values called isocores that are greater than the true stratigraphic thicknesses. If dips are relatively gentle, it is not necessary to correct for the slight difference between isopac and isocore values. However, if the dips are quite steep, the error in the interval may be great enough to affect the placement of contours on isopac maps. As an example, there are many situations in which an actual thinning of strata can be mapped over anticlinal highs. But there are other cases in which the apparent thinning of a formation over structural crests is only an artifact resulting from this type of error. Here we see how production geologists make use of another type of isopac map, which in this case enables us to calculate the petroleum resources in a field. The thickness of an oil-filled reservoir sand is contoured on the map, with the oil-water contact used as the lower reference plane. The area contained between any two contours can be measured with a planimeter and multiplied by the average thickness. The partial volumes obtained this way are then summed to give us the total volume of the oil-filled sand. When this information is combined with measurements of porosity and water saturation from cores or logs, the volume of oil in place enclosed by the structure can be estimated. This example shows how a thickness map can be used to outline simple-shaped bodies of rather uniform lithology. The thickness of the reef limestone facies has been contoured on the Permian Horseshoe Atoll of West Texas. The thickest areas mark the pinnacles at the crest of the atoll, along which most of the petroleum production occurs. In this example from the lower Carboniferous of the Texas Panhandle, 3 combination stratigraphic electric logs show the lateral distribution of multiple thin reservoir sandstones that are interbedded with other lithologies. The proximal facies to the north, closest to its granitic source, contains more of the sands, whereas the distal facies to the south is dominated by limestone and shale. But it is more useful to obtain more detailed information by depicting the composite thickness of the exclusive reservoir lithology over a map area. The exposed granitic rocks and cumulative sand thicknesses greater than 200 feet are found in both the north and east, and the distribution pattern is complex. This is a special type of isopac map, called an isolith map. Basically, it's an isopac map of one lithology only. It can be very useful in illustrating the trends and areal distribution of a reservoir megafacies, as seen on this map. An isolith map is often an important tool in planning exploration strategies. In another example from the Gulf of Suez, an isopac map of the Nukul Formation, which contains several reef and sandstone reservoirs, shows thicknesses up to 1,000 feet. The thickness pattern is irregular as a result of fault block movement. An isolith map of the formations of evaporites shows this lithology to be present only at the south end of the basin, to a maximum thickness of 300 feet. We might wish to create isolith maps for all the major rock types in the formation. We could also summarize the lithologic variation on a lithofacies map. In the Nukul Formation, 3 end-member lithologies have been mapped: sand, shale, and non-clastics. Data from the control wells fall within certain limited fields. Although this map is based on numerical data, it is not, strictly speaking, a contour map. Some facies maps are contour maps in that they express ratios between only two lithologic end members. One ratio commonly mapped is the clastic ratio, which compares the thickness of all clastic rocks in a unit to those of chemical origin. You might want to combine a patterned lithofacies map with an isopact map to get a more complete picture of a formation that's an exploration target. It's often useful to put two or more of these maps together and make what we call compound maps. But now let's look briefly at a few other useful subsurface maps. First, a subcrop map, like this one from northeastern Algeria. It looks just like a geologic map at the Earth's surface. However, this kind of map shows the distribution pattern of rocks beneath the subsurface horizon, usually in unconformity. In this case, we're showing the subcrop beneath the late Paleozoic Hercynian erosion surface. The distribution of this subcrop is important for several reasons. In Algeria, much of the oil comes from Silurian age source rock, shown here. A considerable amount of this oil is found in Triassic sandstones that lie above the Hercynian unconformity, which of course cannot be seen on this map. But Triassic production is concentrated mainly into regions where these sandstones lie above the Silurian subcrop. In other fields, like the supergiant Hassi Massaoud, there has been long-range migration along the unconformity. Although the oil was derived from the Silurian source rocks, as in the case of the Triassic sandstone, it moved up the paleotopographic slope to structural highs, where the unconformity eroded to deep stratigraphic levels and had exposed excellent Cambrian and Ordovician reservoir sands. The map reveals the distribution of these small areas of Cambro-Ordovician subcrop, which have proved to be good exploration targets. If the major reservoir units are concentrated above an unconformity, for instance, channel sands located over deeply eroded topography, the subsurface geologist would find it more useful to map the stratigraphic variation at the level just above the erosion surface. Such a map, which is actually a special type of lithofacies map, is appropriately called a worm's eye view. Let's now look more closely at the Rod El Bagel field of Algeria. As seen earlier from the subcrop map, it lies on an upthrown block and taps a Cambro-Ordovician reservoir sand just below the late Paleozoic unconformity. This field also provides a good illustration of a less common type of subsurface map. This shows a vertical profile of wells across the field. In a sense, it's a structural cross-section. However, instead of showing the position of formations, it is contoured to reflect closely spaced thermometer readings from open-hole drill stem tests. The contours are isotherms, which are lines of equal temperature. At Rod El Bagel, the pay sands are usually hot. They're warmer than beds lying both above and below them. This is because there is an active invasion of water and petroleum fluids from the Silurian source shales, which are still undergoing thermal dehydration in nearby downthrown blocks. Because of this, the isotherms are highly convoluted, and the temperatures are locally inverted. It's impossible to accurately display contours like the 100-degree centigrade isotherm in a map view. Accordingly, we must generalize about warm and cool spots. A structural contour map shows the subsea depth to the reservoir sand and reveals the anticlinal nature of the trap. The line of section that we've just seen runs roughly north to south. Onto this, we can superimpose colored or patterned areas that show the location of warm and cool spots. Warm spots, in this case, are regions where the 100-degree isotherm lies above 2,800 meters. The cool spots are areas where the isotherm is deeper than 3,000 meters. In one small region, because of temperature inversion, both warm and cool spots overlap. This map is significant because cool spots appear to be genetically linked to good reservoir performance. Reservoir performance can be contoured by means of the productivity index. This is a ratio of the volume of petroleum produced over a given time interval to the reservoir pressure drop that accompanies it. The close correlation between high productivity index and cool spots is readily seen. It appears likely that the cool spots are associated with the downward legs of convective cells within the reservoir. Production from wells in cool spots benefits from gravity flowage into the well, and reservoir pressures drop slowly. However, production from wells in warm spots on upward legs of convection currents dissipates some of the heat that drives the circulation cells. The example we've just seen points out another important use of subsurface mapping as a tool of the production geologist. Another example shows the use of subsurface maps to record changes that take place in the reservoir during the exploitation of a field. In this case, the Benton Field of Louisiana. The map shows the isopac thicknesses of a reservoir sand. Natural gas liquids were extracted from this sand, and in order to maintain pressure in the partly depleted reservoir, it was necessary to re-inject the dry gas, along with large volumes of water. In 1950, some of the wells at the south end of the field were changed from their original status and became either gas injection, shown by triangles, or water injection, shown by square wells. The annual progress of the dry gas front, when the first of the injection gas swept into the well bore, can be traced on the composite map, where contours show the annual changes between 1950 to 1959.
There are many other types of maps which can usefully summarize or tie together special categories of subsurface data. Some, such as these, are most beneficial in exploring for new prospects and for making recommendations to lease or to drill. Others are of major value in planning the most efficient and profitable exploration of a field. Today, costs are so high that we can leave very little of the exploration and production process to trial and error.
Now that we have prepared these maps, we ought to know where the oil is.
Well, maybe, but exploratory drilling statistics usually show that the subsurface pictures predicted by mapping and the inferences about petroleum accumulation drawn from them turn out to be wrong about as often as they're right. There's a lot of map making that precedes the drilling of both discoveries and dry holes. And it's the geologist's job to check the well log data that goes into the maps, to make careful correlations between control points, and to honor both the data and the regional model in his mapping. Wrong maps are purely the geologist's fault. Now, in this module, we've looked at the topic of subsurface mapping. We first saw how subsurface data is obtained from cuttings, cores, and various types of well logs. We then explored ways to correlate numerical data from many control wells to provide two-dimensional maps that depict three-dimensional surfaces and units. Some of the most useful of these to the petroleum geologists are the structural contour map and the isopac map. The geologist uses other types of maps, such as lithofacies and subcrop maps, in the exploration task. And in some cases, he may need to integrate several different kinds of data into compound maps in order to obtain a more complete picture of the subsurface. Finally, some regions may have unique problems that require the making of specialized maps. Remember that a subsurface map is only as good as the data going into it, and is only useful if the correlations and interpretations are reasonably correct.
This program has been sponsored in part by the following companies: Egypt, Aramco, City Service Oil and Gas Corporation, Gulf Oil Corporation, Mobil Oil Corporation, Petro-Canada Incorporated, Phillips Petroleum Company, Schlumberger, Standard Oil of California, Texaco Incorporated. IHRDC and the above-listed companies, by their sponsorship, do not in any way guarantee or represent the accuracy of the content or methods contained herein, and the user, upon using this program,